Okay, shut up. So the exam, the class average was about 86, pretty good, percent. If you have any questions about scoring, let me know. I'd be happy to look things over. And I'd be happy to go over, well, two of the questions are just like most of the practice problems you've been doing, but let me go through number 2. That was the one that was the most kind of unusual. And then I have one important issue to go over. The class, I'm planning to do the last exam on Thursday instead of Friday. Anybody that doesn't work for anybody, Friday works better. We can accommodate that. But so here's what's going to happen the rest of the class. So what's left? There's a quiz today. There's an assignment due tomorrow. And then we're not going to have a quiz Wednesday. We're not going to have an assignment due Thursday. So then exam 5 is on Thursday. And if your score for exam 5 is not your lowest score of the semester, then it'll count for itself, and it'll replace your lowest score of the semester. Okay, your lowest exam score. Okay, so how many people here just tentatively think you might want to take the exam on Friday instead of Thursday? Jack? Okay. All right, great. We can do that. Any questions about what's going on this week? Yes?
Can you go over the format of the final?
Yeah, it's going to be just the same as the others. I mean, it's going to be cumulative. We'll have 2 new topics on it. One is going to be internal loads, and one's going to be friction, which is a short topic that I don't know if you've glanced at the assignment problems for that, but there's only a handful of problems, 4 problems or something, I think.
Is it going to be like, I haven't looked, is it going to be like, is it slide or does it type problems? Or?
It's going to be a topic related to screw threads.
Oh, okay.
One related to belt friction, sliding along things. One related to, and then 2 kinds of bearings.
Okay.
So it's not going to be exactly like you might think, just adding friction into the kind of problems we've been doing. It's sort of unrelated to that, although you could make problems like we've been doing with these types of friction in them. Yep.
Is this going to be worth more points than the other tests?
No, they're all worth whatever it is, 12%. Each one's 12%. So it's just one more, a little farther. But it's still cumulative like all the other ones. It's still just 2 hours.
Okay.
Okay.
So is it like focus mainly on internal loads and friction, or is it just like...
Well, I have to get some of those questions in, so it's going to be heavier than the other stuff. But the idea is it's a cumulative test up to this point. Any other questions? Okay. Let me go over number 2 on the exam. No. Yes. It's not 2. What is it? 4, number 2. So here's number 2 on the exam. You have, bless you. You have to go back to some particle stuff, and then you also have to deal with a bunch of different angles kind of going on at the same time. There's a 45-degree angle here. there's a pin and slot joint up here where this is 20 degrees from the vertical. And then there's a little cart thing sliding along a 60-degree angle like that. This is 100 kilograms. This is 20 kilograms. And the first question is, what's the cable tension? And then the second question is, what are the reactions for the beam? Okay, so the way the questions were asked was meant to kind of lead you in the right direction. So first, to figure out that cable tension, isolate the particle, isolate the box, the cart. Okay, so there's the cart. There's a weight force of 981. There's a normal force, and there's a tension force. This one is just in the negative y direction. This one, well, let's think of the tension first. So this angle is at 60 degrees. This normal force is, you can get there by going from the positive x-axis to the direction of the tension, and then another counterclockwise 90 degrees. So 60 plus 90 gives you 150 for that normal. So that angle's 150. So Newton's second law says 0, negative 981, plus t times cosine and sine of 60. So 0.5 t, 0.866 t. And then plus n times cosine and sine of 150. So that's negative 0.866 n, positive 0.5 n is equal to zeros. That's two equations for two unknowns. You can solve it and get that t is equal to, I think it was about 850. You can also calculate the normal force, but I didn't ask for that specifically. And now that you have that tension, now you can isolate the beam. The free body diagram looks like this. You have a pin joint down here, so I'll call that reaction force. It's a full force vector. I'll call it RA. Then there's a weight at the midpoint of 20 times 9.81, so 196.2. And then there's a cable tension that's pulling in that direction. And let me make it clear that that's not perpendicular to the beam. That is at that, that has to do with that 60-degree angle. And since it's a single cable, the force is the same, so that's whatever you got in the other one, about 850. And then there's the pin and slot force that's not lined up with the beam. That makes an angle of 20 degrees here. And I guess from there, I think I'll just stop there. But now you just write out the table, write out Newton's laws, and calculate. You have, oh, I didn't put a label on this. Let's call that RB. That's a scalar. So you have 3 equations, Newton's second law and the rotational equation, 3 unknowns from RA, x and y components, and then RB. And you can solve it. Any questions about that? Here, Joey. Thank you. All right. Well, last time we did, so going back to internal loads. Last time we did an example problem that was like this. This time we're going to do an internal loads problem like this.
Quick question, please.
Yes.
Since you said that we're going to cover friction on the class exam, does that mean that we're going to have homework for friction due tomorrow, or no?
No, it's not going to be due, but you'll just have to, prepare on your own with the practice problems. Okay, so you look at that, and it looks like it's probably basically identical. We're going to see that working from the left, it's not identical. And so Alani, of course, more than anybody else, is like, well, I'm going to do it from the right, because that's her obsession. But you could, of course, do problems where you could see problems where there's one like that, and then what are you going to do? So you got to learn how to do this. Okay, so what's the difficulty? This is harder. Why? The reason is so this is your beam, and where I drew the end of that black line, let's say that's where we're doing our cut. And let's say our distributed load looks like this. When the triangle is facing this direction, when we did our cut, we just got a smaller triangle, right? When we do the cut this way, it chops off the identity of the triangle, the thing that makes it a triangle. It chops off its point, And so now we have this trapezoid we have to deal with. And it's just kind of a mess. I mean, we're going to think through it the exact same way, but we're going to have to deal with a little more complicated geometry. Okay, so the way we're going to do this is we're going to break up this trapezoid into a triangle. Sitting on top of a rectangle. The value of let's say the height of the rectangle is equal to our function q, that for any x value gives us the height of the distributed load. If we call this value, I don't know, call that capital Q. Is that getting too cute? Okay, so then the height of this triangle, what is it? Yeah, capital Q minus that function Q. The width of both the triangle and the rectangle is x. And so we end up with one point force when we go from the distributed load to a point force acting at the centroid of the triangle. I'll call this area of the triangle. And another point force acting at the center of the rectangle. Okay. None of this is like horribly hard to understand or anything. It's just more steps. Any questions about the thought process on this? Okay. Well, let's just do an example. What?
Are we going to have 2 point forces?
Yeah, so you could combine them by finding the centroid of the trapezoid and the area of the trapezoid, but there's no benefit to it. So you might as well just treat them as two separate. So instead of representing it as 2 point forces, as 1 point force, we're just going to represent it as 2, and it works the same way. Okay, so let's say we have a cantilever beam coming out from the wall on the right and a triangular distributed load with a maximum height of 5,000 newtons per meter and a length of, let's make this 2 meters. What are the internal loads? So what do you think when you see a cantilever connected to the ground on the right side? Yeah, you can just go straight to internal loads because that's not going to come into it. So you think like, Yahoo! Okay, so we can go right to the cuts. And there's, how many cuts are there going to be? Just one, because the only places where the subfunctions are going to change are the two endpoints. N is 2, so you just have one cut. So x is going to vary between 0 and 2. And so there's the isolated piece. There's still part of the beam that I'm not drawing over on the right. And so the distributed load looks something like this. For any x value, it looks qualitatively like this. So there's the distributed load, and it's 5,000 over here because we always include all the way to the left end on our isolated body. And then T, V, and M. All right, well, let's think about this trapezoid. The first thing we have to do is come up with an expression for the function Q that represents the height of this, that represents this line function. So Q as a function of x is equal to mx plus b, right? It's a line. What's the y-intercept? When x is equal to 0, what's this equal to? Yep, so it's equal to mx plus 5,000 with the triangles going the other way, when x was equal to 0, q was always equal to 0. So this is the first time we've had a y-intercept. And then what's the slope? Yeah, it's rise over run. The rise is negative 5,000. The run's 2. So this is negative 2,500x plus 5,000. Okay? Because, so when you're doing there's a couple ways to think of it. You know, anything that's below horizontal has a negative slope. You can think of the slope as rise over run, and this as x increases, this y value is actually dropping. So you can think of it as, so go out to here, go out 2 meters, you have a value of 0 minus 5,000 divided by 2, and so you get negative 2,500.
Is this the function for rectangle?
For what?
Rectangle or the triangle?
This is the function that tells you this point. So if this is x, this is the height of the rectangle. And then the height of the triangle, so that's also this, negative 2,500x plus 5,000. So the height of the triangle then has to be equal to 5,000 minus that expression. And the 5,000s cancel, and you just get positive 2,500x. Any questions about where any of those values come from? Okay, so the area of the triangle is 2,500x, that's the height, times the width, divided by 2, so 1,250x squared. And what's the location of the centroid of the triangle? Yep. And then the area of the rectangle is the height, which is negative 2,500x plus 5,000 times the width. So you get a value of, I'm going to write it as positive 5,000x minus 2,500x squared. And what's the centroid of the rectangle? Yep, that's just right in the middle of that rectangle, so x over 2. And now I can redraw this free body diagram. We have a force acting at the midpoint with a value of 5,000x minus 2,500x squared. Then we have a force a third of the way along the beam of 1,250x squared. And then we have the internal loads, T, V, and M. Nope. Nope, this is it. So once you figure out how many cuts you need at the beginning, that's the number of cuts you need no matter what happens inside the cuts. So Newton's second law says Okay, now we have to be a little careful with these signs. This thing, this funny looking thing, is actually always going to be positive. You can plug in 2 and see that that's true. You know, plug in 1.99642, see that it's true. So this is a positive number with a unit vector down. So when we represent this as a vector, we're going to have 0 and then negative of this thing. Okay. 1250x squared is a magnitude. This is downward, so we're going to have 0, negative 1250x squared. I'm going to, well, I'll just write the negative in there. So negative of the quantity 5,000x minus 2,500x squared. And then plus t plus 0 negative v. I'm just going to combine those two into t negative v. We get an internal tension of 0. And then v, the ugly one, says, what do we have? Negative 3750 x squared. You're right. Yes, negative of a negative. So 1250 x squared minus 5,000x. And then the moment equation. What's the moment arm of the 1250x squared? Yep, x over 3 times 1250x squared. And then is that clockwise or counterclockwise? Clockwise, so that's negative. And then what's the moment arm of this thing? X over 2. The magnitude is 5,000x minus 2,500x squared. And is that clockwise or counterclockwise? Clockwise. And then we have plus m minus vx is equal to 0. So m is equal to vx plus, what's 1250 divided by 3? That's got to be positive 416.6 repeating x cubed. And this is plus 2,500x squared minus 1250x cubed. This is cubed. No, this is, the 2,500 should be squared. Okay, and now multiply the function that we got for v by x. To simplify this, we get 1250x cubed minus 5,000x squared plus 416x cubed plus 2,500x squared minus 1250x cubed. Well, these two cancel out. And you get negative 2,500x squared plus 416.6 repeating x cubed. Okay, we can check the derivatives. Dm dx needs to be equal to v. That one works. That one works. Okay, good. And then if you take the derivative of v with respect to x, you need to get that function little q back. So this says 2500x minus 5,000 and 25. Do we have the signs right?
Derivative v is
Negative, right. So, so yeah, positive 2500x minus 5,000 multiplied by negative 1, and you get q back. Any questions about that? So those are tedious. That takes a lot longer than if the triangle's facing the other way. The other kind of problem that, so the last internal loads topic is internal loads in structures. So the only thing that changes when you're dealing with a structure is that the member you're looking at isn't already horizontal. And we've only done these calculations, internal loads, when the beam is horizontal. So what you have to do is choose a new coordinate system. Okay, so what's the issue? So let's say that you're starting with this structure. You solve the structure for the external loads. And you get something that looks like this. You solve for this vector RA up here. You solve for a force vector F12 here. But now how do you go from this? So now you have values for these. But how do you go from this to calculating internal loads? There are a couple ways you could do it. I think the harder way would be to leave it in this orientation and then choose unit vectors going in the direction of t and v and m and do the calculation that way. Instead, so if our coordinate system is oriented like this, once we've solved it, we have a coordinate system like that. If we could re-express all of these vectors in terms of a coordinate system with the x-axis pointing along the beam, then we can do it the way we're used to. So we're going to use a rotation matrix to re-express these force vectors in a coordinate system with the x-axis along the beam. In this case that I just drew, we want a rotation matrix that goes from this to this. Then you can just draw it horizontally. The way that you draw it doesn't matter mathematically. Mathematically, all that matters is the relationship between the forces and the coordinate system. So then we can draw the beam horizontally like we're used to. Okay, so here's an example. So let's say that there's a beam that makes an angle of 30 degrees with the horizontal and makes frictionless contact with the wall. And let's say this is 1,000 newtons acting down. Let's call this half a meter. What are the internal loads of this beam? I'm going to neglect the weight on this one. Well, I'm going to neglect the weight in any examples I do in this topic, because if you don't remember, the weight acts like a distributed load, and we'd have to deal with rotating the distributed load, which actually is surprisingly similar to this, but we got to stop this analysis somewhere. If you're curious about it, I'd be happy to talk to you about it. You might be able to just figure it out on your own, how you would deal with weight in this case, but we're going to be neglecting the weight on these. And notice that even though this isn't really a structure, this problem includes the difficulty that internal loads and structures has. We're starting with a beam that's not lined up with our coordinate system, and so once we find the external loads in a coordinate system like this, we're going to have to re-express it in a coordinate system where the x-axis points along the beam. Okay, so free body diagram, we have the reaction force there, I'll call it RA. We have a weight force of 1,000, and then we have the frictionless contact. I just want to make this look horizontal. Call that RB. We know the direction, so that's a scalar variable. I've noticed a few people starting on tests to skip the first two columns of this table. That's great if that makes sense to you. If you can just look at it and figure out what that row vector is going to be, that's great. In fact, I think if you have time, see if you can figure out how to do that, because I think it gives a helpful insight into what that row vector is, you know. Okay, so the origin is down here at A. So for that force RA, we're at the origin. I'll make that the about point. So there's no row vector. Force vector is RAX, RAY, and so there's no moment. Then up at B, we're at the point 433.25. That's also the row vector anytime the about point is the origin. The force is negative RB 0. And so you get positive 0.25 RB. And then the midpoint is 0.217, 0.125. The force vector is 0, negative 1,000. So you get negative 217. Maybe I'll make this 16.5. Okay, so Newton's second law says RAX, RAY plus negative RB 0 plus 0, negative 1,000 is equal to zeros. The moment equation says 0.25 RB minus 216.5 is equal to 0. That gives RB is equal to 866, right? And then what's RA?
866.
The X is 866? Yes. And then Y?
1,000.
Okay. By the way, I don't usually notice this stuff, but on the last exam, there must have been 10 different people who got the equation 0.5, like 0.5 R is equal to 100, and said R was 50. It was the weirdest thing I've ever seen. Like, I mean, I don't really have any insight into that, but like over and over and over again, like I was like, oh shoot, we forgot to cover algebra 1. Okay, so if we go back to the body now that we've calculated these loads, we have the 1,000 acting there. We have 866 this way. And then here we have 866, 1,000. All right, so what we want to do now, we have it like this. We want to figure out what rotation matrix we have to apply so that we can re-express all of these force vectors in this coordinate system, where this angle is 30 degrees. Okay, well, what we need to do that is our theta, to go from here to here, is that a clockwise or counterclockwise rotation? Okay, so this is equal to positive 30 degrees. Our rotation matrix is cosine theta, sine theta, negative sine theta, cosine theta. And so we get a matrix of 0.866, 0.5, negative 0.5, 0.866. And now one by one, we're going to re-express these force vectors. So we're going to re-express the force vectors in the new coordinate system. Okay, so the first one, let's do, what did I call it, RA? Let's do RA. So we have the Q matrix, 0.866, 0.5, negative 0.5, 0.866, times our old expression for RA, which is 866, 1,000. You don't really need to know how to do this. Your calculators will do it for you, but if anybody has any questions about this, let me know. But that is I think that's 1.25, or that doesn't make any sense. 1250. And then, what's this one? Positive 433. That's RA expressed in the new coordinate system. And let's think about this. Think about what this vector looks like for a second. So if you had, so I'm going to start with the old coordinate system. Thanks. Okay, there's the old one. So this vector looks like this. Something like that, right? Now we want to come up with the components of this vector in a coordinate system that looks like this. So what would you expect to happen to the x component? Would it get bigger or smaller? It should get bigger. And what should happen to the y component? Smaller. They're both still positive. Can you visualize what I'm talking about here? No? Okay, so now let's do the 1,000 Newton force.
Why wouldn't X be smaller and Y be smaller?
Okay, so here is the projection onto X of the old. Okay, here's the projection onto X in the, so you're comparing this length to this length, and because of the precision of my drawing, you can tell that this is longer. Okay, so now the 1,000 Newton force. So we take the rotation matrix, 0.866, 0.5, negative 0.5, positive 0.866, and multiply it by the vector 0, negative 1,000.
You just assume that it's going to be the same as the 1,000 Newton force from that end of the same coordinate system from the rotated end, and gave you the negative sign for that. Isn't that true? So we got 1250 and 433.
Mm-hmm.
So if you were just to say negative 433, then
I don't know. I don't follow why you would. Let's talk about that later, okay? I'm not sure. So now look at this 1,000 Newton force. That's acting in the negative y direction. So if you express that as a force vector, the components are 0, negative 1,000, right? So we're going to multiply 0, negative 1,000 times this rotation matrix. And even I can do this one. That's negative 500, negative 866. Okay, so let's visualize this one again, because it went so perfectly last time. Okay, so there's the old coordinate system. This vector is this, right? So now what happens if we want the components in a new coordinate system like that? Well, first, what quadrant should it be in? Should be in the third quadrant. Both components should be negative, and we have that. And then, I don't know. That might be about all the eyeballing we can do on this one. But and then the last one is that force vector that I called RB. So we're going to take the rotation matrix, and multiply it by the vector RB, which was, what are the vector components for this? Negative 866, 0. And so that is negative 750, positive 433. So let's think about the components again and make sure that those signs make sense. If we start out in this coordinate system, and the vector that we're looking at is this, and then we re-express it in that coordinate system. What quadrant should the vector be in the new coordinate system? Second, so it should have a negative x component and a positive y component, and that's what we have. This is the first, second, third, fourth.
So the vector itself doesn't rotate?
The vector stays there and the coordinate system moves. Okay. That's right. So yeah, if you look back at all those examples, that's what's going on. Okay, so now what we have is this. We have a beam where our force vectors now are expressed in this coordinate system. And the values are 1250, 433. For the middle one, negative 500, negative 866. And for the right end, negative 750, positive 433. And now what do we have to do in order to draw this horizontally? We just have to draw it horizontally, because it's all we have to do now is turn our head. You know what I mean? So the mathematical part of it was getting the coordinate system and the beam to have the same orientation. Now we can draw it however we want, you know. Okay. Well, let's take a break there. Come back, and I'll do this problem, and then if we have some time left, we'll start talking about friction. Okay. So let me just finish this problem. But one thing that all of these have in common is by the time you get to the point of having all of those forces re-expressed, it's a really easy internal loads problem because we're not dealing with any distributed loads. Okay, so how many places are there where the subfunctions can change? N equals 3. And so how many cuts do we have to do? 2 cuts. Okay, so cut 1. What did I say the length of this was? 0.5. So cut 1 is going to go from 0 to 0.25. So we have 1250 and 433 on the end. And we haven't gotten to the next force yet, so then we just have the internal loads. So Newton's second law says 1250, 433 plus T negative V is equal to zeros. So T is equal to negative 1250 and V is equal to 433. So is this in tension or compression? Compression, yep. It's called T because positive is tension. If it's negative, the thing's in compression. The moment equation says M minus Vx is equal to 0. So M is equal to Vx. So M is equal to 433x. And then cut 2 is valid for x values between 0.25 and 0.5. We still have the forces at the end. Now we also have the ones in the middle. That's negative 500, negative 866, I think. And then we have the internal loads. So Newton's second law says 1250, 433 plus negative 500, negative 866 plus T negative V is equal to zeros. So T is equal to negative 750. And V is equal to negative 433. And the moment equation says, okay, so we have a downward force of 866 with a moment arm of 0.25. And would a downward force make this rotate clockwise or counterclockwise around this point? Clockwise, so this is negative plus m minus Vx equals 0. So m is equal to 216.5 minus 433x. And so now what we have is the ability to start with a structure, this complicated thing where, you know, they can, very often you don't really have any intuition about what kind of external loads are acting on them. You can solve those external loads and then go in and figure out where on this structure you're most worried about this thing fracturing, which is, you know, kind of a satisfying ability. Imagine you start with some wacky structure like the, you know, those pliers, any one of those complicated structures problems. Now we can follow it all the way through and figure out where the internal loads suggest that we want to be careful if we're designing this object. What we can't do, like I said, is distributed loads, but it really isn't that much of a jump from where we are to being able to do it with distributed loads too. Yep.
If you had a two-force member,
Mm-hmm.
for example, that those two triangular structures.
Yeah.
So if you were to solve for one of them, would you be able to say that the other one is the negative effect, or is that just
No, not necessarily. But what you can say with a, so okay, so say we had this thing. Let's call this member 1 and this member 2. What do we know, without doing any calculations, what do we know about the internal loads of members 1 and 2? In this case, they are equal and opposite. That, I don't think that's a, like generally you don't know that that's true in a structure like this. But this structure is made up of two force members, right? Yeah, and so in this case, yeah, one's in tension, one's in compression. The thing I want to get at here is two force members can't have any shear force, can't have any bending moment. All they have is, you know, by the nature of what tension and compression is, all they can have is a internal tension or an internal compression. And that's all cables can have too, is an internal tension. So if you did this calculation, calculated the external loads, rotated the coordinate system, redid all this stuff, calculated the internal loads, you'd always see, if you did it right, that the shear force is 0 and the bending moment is 0. That has to be the case with two force members. All right. Well, I want to do one really, so the next thing we're going to talk about is friction. Yes?
So if you had two beams that were perpendicular to each other,
Mm-hmm.
straight up and straight down
Yeah.
and straight left and right, would you have to turn one of them equal to solve, or can you solve
to do the internal loads. You always could do the internal loads like this. So if you had a member like this and you wanted to calculate the internal loads, and you had all your forces expressed in this coordinate system, and you didn't like rotation matrices, you know, because like some people like different stuff. You don't like that. So you could define tension that way, shear force that way, bending moment that way, by multiplying these scalars by unit vectors in those directions, and then do the calculations the same way.
I'm saying if you have two of those.
Yeah.
Do the same. Okay.
Yeah. So yes, you can do that if they're perpendicular. You can do it even if they're not. But I tend to think, I mean, I've said this a few times in a few different settings. I tend to think I want to do every problem the same way as much as possible. So I like approaches where you take something, turn it back into the thing you're used to, and then use the method that you've used a million times. To me, that makes it easier to avoid mistakes than thinking about stuff fresh every time, you know what I mean? Okay, so with friction, we're going to talk about these things. We're going to talk about square threaded screws, it's a type of threading that you use for really big loads, like in jacks. And we're going to talk about belt friction. And we're going to talk about bearings, two types. Journal bearings, which are like pin joints, and thrust bearings, which is like the clutch on a car. I'll draw pictures of those when they come up. But so these are the topics we're going to do, and this is going to be the first one, square threaded screws. And square threaded screws, the calculation is based on something you did a bunch of times in Physics 1. It's sort of, I think the most interesting thing about it is how you get from the actual square threaded screw to this kind of analysis. But for doing the problems, this is the kind of problems we're doing. Analysis of blocks sliding on inclines. So for example, let's say this is 20 degrees. You have a box with a mass of 100 kilograms. You have a coefficient of static friction that's equal to 0.4. Will the block start to move? The way you did this in the past was you used a coordinate system that had the x-axis oriented along the incline, y-axis pointing out of the incline, and then you had to use trigonometry to come up with the components of the weight force. The weight now is, isn't just perpendicular to the axes. And that's how we're going to do it here. So we have a weight force of 981, a normal force like that, a friction force going opposite the direction that the thing would accelerate if there was no friction. So in this case, the friction is going to go this way, and we'll assume that that's equal to mu sub s times the normal force. And Newton's second law says, for now I'll write it as the weight force plus 0n plus mu s times n, 0, is equal to 0. And the trickiest thing about this is expressing the weight force. So I just want to point out that you can use the rotation matrix to express the weight force now. Once you get used to doing it in your calculator, it's faster than thinking about the triangle. So let's use the Q matrix to re-express the weight force. So we know, the weight force is really easy to represent in this coordinate system, and now we want to re-express it in one rotated like this. So what's the theta for the rotation matrix?
20.
Yeah, plus 20. So Q is equal to 0.94, 0.342, negative 0.342, 0.94. And so mg expressed, I'll write it like relative to the new coordinate system, is equal to 0.94, 0.342, negative 0.342, 0.940 times the weight force in the old coordinate system, 0, negative 981. And you get a value of like negative 335, negative 921.8. Plug that in for the weight force, and then you solve. Okay, so next time we'll talk about how to take a square-threaded screw friction problem, and put it into this form. Yes.